Welcome to all of you on my channel Physics Hub. Today is 18th November 2018 Sunday, and it's the time for a new set video. As you know that we upload a set video on every Sunday, and it usually consists of 10 solved problems on different topics of physics. We generally upload the question paper few days before the day we upload the solution on YouTube, so that you can try to solve the questions and match your answers on Sunday. One thing, whenever we upload a said video, we distribute, or any kind of video, we distribute it to different relatable playlists, as you can see here. So go through the playlist and you will be able to get videos as per your choice. Now, before to discuss today's said video, let me tell you something. Yesterday I have made a video entitled 30 topics to prepare in the last 30 days before CSIR-NET exam. There I have covered almost all frequently asked topics in CSIR-NET physics exam. Please go through that video. It will easily help you to get 90 to 100 marks in your NET exam. Link is in the description. Look, hopefully you all are solving questions, reading different topics. One thing I would like to tell you here, that keep a quality time for revision, read, practice, revise, and try to give full length tests in this last month. Later on I will make a video on how to make proper utilizations of the 3 hours of CSIR-NET exam on the day of examination. Now let's start today's set video. So this is set 18, and this set is based on questions from numerical analysis and Green's function. Both these two topics are very important. So in different papers you have seen that one question from numerical analysis and one question from Green function come in part C of 5 marks. So 5 plus 5, 10 marks. So if you understand this paper, you may get 10 marks in your CSIR-NET exam. So let's start with the first question. So the first question reads, in finding the roots of the polynomial f of x equal to 3x cube minus 4x plus 5 using the iterative Newton-Raphson method, the initial guess is taken to be x equals to 2. In the next iteration, its value is nearest 2. Okay, so the function is given here. Now from Newton-Raphson method we know that xn plus 1 equal to xn minus f of xn by f prime xn. So if xn is some value and xn plus 1 is the next iterative value. Okay, so f of x is given. Now f prime x we found out 9x square minus 4, taking single derivative. Now initial guess is x naught equals to 2. This is basically root. Okay, so the initial root, suppose I am taking it to be 2. Then we just calculated the value of this function at x naught equals to 2 and f prime at x naught equals to 2. Then we get value 11 and 32. Now what we do to get the next iterative value, we will put these values in this first equation, and x naught is the initial guess and x1 is the next approximation, means it is more correct than this initial value. So 2 minus 11 by 32 equals to 1.656, and next iteration means we have to do one iteration. If the question asks you to do 2 or 3 iteration, then you have to apply this formula twice and thrice. Suppose you get after first iteration this value, and if you are asked to calculate in second iteration, then what you will do in the next formula, you will just put this value here and you will calculate the value of f of this and f prime of this at this point. Then you will get the next iterative value. For the time being, they have asked only 1 for 1 iteration. That is very easy, and it is matching with option 2. Now coming to question number 2, the value of the integral 0 to 8 1 by x square plus 5 evaluated using Simpson's 1/3 rule with h equals to 2 is. Now before solving this question, we should know what is this Simpson's 1/3 rule. So according to Simpson's 1/3 rule, I have written the formula in general so that you get it very clear. So a to b f of fx dx equals to h by 3 into y naught plus yn, means suppose this is the 0 value and this is this is the range of the upper range, and this has been divided into n intervals. N must be even. Okay, then this is the value where the function value is y0, and at this value at the end the value of the function is yn, and it is divided into n intervals, and the intervals number of intervals is even. Then h by 3 into y0 plus yn plus 4 into sum of odd terms y1, y3, y5, etc., plus 2 into sum of even terms, as you can see from the formula. So here in this question, what we are given the value of a to be 0, b to be 8, and h means the step size is given to be 2. So you have to divide the interval 0 to 8 with a step size of 2. So it will be divided into 4 sections. Okay, 1, 2, 3, 4. So we have made the table, and before making the table we just found the value of n, means in how many intervals we should break the space. So we have to break the interval into 4 parts. So 0, 2, 4, 6, 8. So it's basically 4 parts, and we found the corresponding function value at these points, and it is listed here. Now we calculate y0, y1, y2, y3, y4, and how they are calculated I have shown you explicitly, so you will be easily understand. Okay, so 0 to 8 1 by x square plus 5 dx equals to h by 3. H is we found or it is given 2, so 2 by 3 into y0 means 1 by 5 plus yn means last value 1 by 69 plus 4 into even odd terms means y1 here, and y3 are the odd terms, so 1 by 9 plus 1 by 41 plus 2 into even terms, only one even term is there, so 2 into 1 by 21, and if you calculate it you will get 0.565, and is matching with option 1. Now coming to question number 3. Consider the differential equation dy dx equal to x square minus y with the initial condition y equals to 2 at x not x equal to 0. Let y1 and y half be the solutions at x equal to 1 obtained using Euler's forward algorithm with step size 1 and half respectively. The value of y1 minus y half by y half is. So this question is basically very easy, and you have to use Euler's forward algorithm. Now before solving the question, let me tell you what is this Euler's forward algorithm. So I have written it: y1 n plus 1 equals to y0 plus h by 2 f of x naught y0 plus f of x1 y1 n. This n plus 1 gives you the number of iteration. Okay, and n goes from 0, 1, 2 and 3 dot any integer values it will take. Now to apply this formula we should have assume some approximation. Okay, for the time being we are assuming, but it can be proven. So where y1 of n is the nth approximation to y1. This iteration formula is started by choosing y1 1 from Euler's formula. Look, Euler has given two formulas, Euler on simple Euler's formula, and this one is Euler's modified formula. Okay, so in general you should apply Euler's modified formula, and the Euler's modified formula is started with Euler's formula, which is given by y1 of 1 equals to y0 plus h into f of x naught y0. X naught y0 are the initial values which you are given. Okay, so step size, so we have to calculate the value of y at x equal to 1 using step size 1.5. So first we are calculating with step size 1, h equals to 1. Then f of x naught y0 we find out from, because this dy dx is f of xy, x square minus y. So we are calculating f of x naught y0. Here x naught is 0 and y0 is also y0 is 2. This is the initial condition at x naught y0. X naught is 0, y0 is 2. So f of x naught y0, if we put the value of x naught y0 to be 0 and 2, we'll get minus 2. Then y1 from, which is found from here, then we found y1 equals to y of 1. Look, we are asked to calculate the first iteration. That's why we don't have to use this formula. This is the general formula, but this is the specific formula which is used for the first iteration. So for the first iteration we get y1 to be 0, and which is denoted by y1, this value. Now we are calculating with step size h equals to half. So if we calculate y with h equals to half, we get 1, and we are asked to find out y1 minus y half by y half. So we just put the value 0, then minus 1 by 1 equals to minus 1, and it is matching with option 2. Moving on, question number 4. The integral 0 to 1 root over x dx is to be evaluated up to 3 decimal places using Simpson's 1/3 rule. If the interval 0 to 1 is divided into 4 equal parts, the correct result is. Now, as I have already introduced Simpson's 1/3 rule, a to b f(x dx) equal to h by 3 y0 plus yn plus 4 into odd terms plus 2 into even terms, and the number of intervals must be even. Then what is given here, n is given to be 4. Last time we had to calculate, but here they have already given a0 equal to 0, b equals to 1, and f of x equal to root over x. So everything we are given. Now what we have to do, we have to calculate h. So h equals to b minus a by n. The last problem we h was given and we found n. Now n is given, we have to find h. So accordingly we found out h, and we just put the values after making this table. And I have already shown you how to make this table, so you just check it out. And what we have put, h we have got 1 by 4, and then 3 h by 3 plus y0 is 0, yn equals to 1, and 4 into these odd terms yn and y3 plus 2 into this even term y2, and after simplification you will get 0.657, which is matching with option 3. Now coming to question number 5, find f15 from the given table. So as you can see, this the table has only 5 values, and this f of 15 means the value may reside at this position, means at the beginning of the table. So you will use Newton's forward interpolation formula here. Now look, Newton has given 2 interpolation formulas, forward interpolation formula and backward interpolation formula. We will use forward interpolation formula when the value to be determined is at the beginning of the table, and if you have to find out some value which is lying at the end of the table, then you should use Newton's backward interpolation formula. And as far this problem is concerned, we have to find out f15 which is lying at the beginning of the table. So we are using Newton's forward interpolation formula, which is given by this: Pn of x equal to y0 plus u into delta y0 plus u into u minus 1 by 2 factorial delta square y0 plus u into u minus 1 into u minus 2 by 3 factorial delta cube y0 plus dot dot dot, where x equal to x0 plus uh, therefore u equals to x0 x minus x0 by h. Now what are the values we are already given? X equal to 15, so at that point we have to find out the value. X0 means the initial value is 10, h is 10 because 10, 20, 30, so interval is 10, so h equals to 10, step size is 10, therefore u equals to 15 minus 10 by 10 equals to 0.5, so we have already got u. Now to apply this theorem, we need to determine these values, delta values. So to determine the delta values, we should construct forward difference table. And the forward difference table looks like this. So here we have written the values of x, and here in this column we have written the values of y. Now the delta values are found out in this way. Look, this is delta y1, means y1 minus y0. Then when you will calculate this value minus this value, which basically the formula is yn plus 1 minus yn. Okay, so 66 minus 46 20, 81 minus 66 15, 93 minus 81 12, 101 minus 93 8. Now for the next delta value, we just repeating the same thing. 15 minus 20 minus 5, 12 minus 15 minus 3, 8 minus 12 minus 4, and in this case also minus 3 minus of minus 5 means plus 2, minus 4 minus of minus 3 equal to minus 1, and this is calculated in the same way. So we just got everything whatever we need to apply this formula. Okay, so Pn of 15, we just put the value of x to be 15 and value of u to be 0.5, and delta values we get from here. So when you are applying Newton's forward interpolation formula, the values we should take is like this. The values will come like this. Okay, and when you are applying the backward interpolation formula, the value will go like this. Okay, so 20 we take, then minus 5 you took, 2 you took, and minus 3 we took. So it is coming in this way. Now when you will be applying backward interpolation formula, the values will go like this from lower portion, and upon applying the value, you will get 56.8672, and it is matching with option 3. Now coming to question number 6. Apply Runge-Kutta method to fourth order to this equation 10 dy dx plus equals to x square plus y square, and find y at 0.1 given y at 0 equals to 1. Okay, to solve this problem, we just see that this is the equation we are given. So if we have to find out dy dx, which is f of xy equals to x square plus y square by 10. Now what are the things we are given? H equals to 0.1 here, because you are given at the value at 0 and you have to find out at 0.1. So here h we take 0.1, and x naught is 0 at y naught equals to 1. So the initial values are given. So we have to apply Runge-Kutta method. So before applying the Runge-Kutta method, we should know the formula. So in Runge-Kutta method, the formula is y at the next iteration. Suppose you are given this initial value, the next iteration equals to y naught, means initial value, plus h by 6 into a plus 2b plus 2c into d. This is the formula. Now how to apply this formula, I will be showing you one by one. Okay, so first of all we calculate a. The constant a equals to f of x naught y naught, means the value of the function at initial values. So if at 0 1, so 0 1 we put this in this part, so you will get 0.1. Next we have to find out b. The formula for b is f of x naught plus h by 2 plus y naught plus h into a by 2. So if into 0.1 by 2 into 1.005. Look, in different books the formula is given little differently. Look, here we have already we did not multiply h at this position, but in some book you will find that h is multiplied, but at the while applying this formula they will not multiply h here. So here we are multiplying with h, so here we are not multiplying with h. So b equals to f of x naught plus h by 2 plus y naught into h into a by 2. So x naught plus h by 2 means 0.1 by 2. X naught is 0, h is 0.1, so 0.1 by 2, and y naught is 1 plus h into a by 2. A equal to 0.1 by, then 0.1 by 2 into h. So 0.1 into 0.1 by 2, you will get 1 point, and with 1.005. So the modified f values are 0.05 and 1.05. So we will put these two values here in this expression, and you will get 0.1012525. Similarly, the formula for c is given by f into x naught plus h by 2 plus y naught into h into b by 2. Here you have to find out, we have to put the value of b from here. Okay, so accordingly we calculated and we got 0.1012650088. And d, look, in the expression of d it is noticeable that it is not multiplied with c by 2 or h by 2. It is directly multiplied with x naught plus h plus y naught plus h into c. So many times students make mistake here, so be careful while you are calculating d. Okay, so d will calculate and will get this. So y at 0.1 equals to 1 plus which is 0.1 by 6, and you got value of A, 2 into B plus 2 into C plus D, and we'll get 1.0101345112. So it is matching with option 1. Look, we are practicing this problem, so we have taken this clumsy calculations, and as you know that in CSIR-NET exam calculators are not allowed, so you will be given easy values so that you can calculate it manually, or if some clumsy calculations are included in your calculation, then the values will be provided to you. Don't worry, you just know the process how to do it. Okay, so this is for fourth order Runge-Kutta method. Okay, so sometimes you may be asked to apply second order Runge-Kutta method. Okay, that is quite easy, but you should know about these two order, means fourth order and second order also. Going to question number 7, consider minus y double prime equals to f of x, y naught equals to y1 equals to 0. The corresponding Green's function is. Now the questions related to Green's function started. So look, I have already made videos on Green's function. You can check our playlist, and the link is then given in the description for the Green's function video. You can check it out, Green's function video 2 and video 1, then you will be able to understand. So what we do, whenever we are given a differential equation of second order, we just write the homogeneous form. So minus y prime equals to 0. Homogeneous means the right hand side is 0. Okay, so from this we will be calculating the solution in the form c0 plus c1x. Now we have to calculate, we have to find out two function values, y1 and y2. Now this y1 and y2 is determined depending upon the boundary condition. The boundary condition says y0 and y at 1 equals to 0. So look, y1 equals to x, then only it will be y1 at 0 equals to 0. If you take y2 equals to 1 minus x, then you will apply this boundary condition, y at 1 should be 0, so it should be y minus 1 minus x. So this is a check, and in this way we can calculate the two values y1 and y2. And as when you know y1 and y2, we have to find out the another a constant a of Green's function, and the formula for this is 1 by p of t y2 prime t y1 t minus y1 prime t y2 t. And what is p? P into dy dx. Okay, so but there is no p, x is the coefficient of dy dx, but here p of t is the coefficient of this double prime, y double prime. So here the coefficient of y double prime is minus 1, so p of t is minus 1, and y2 prime t. Okay, so y2 is 1 minus x, y2 prime equals to minus 1. So minus 1 into y1 t is x minus 1 into 1 minus x, so you will get 1. Okay, here we have written in terms of t. This formula is for t, but here we are dealing with x, so we have placed by the t by x here. Okay, now the Green's function is given a into y1x into y2 t, a into y2x into y1 t. Now the value of a is 1, so it doesn't matter, so 1 is removed from here, and y on x is x, and y2 t 1 minus t. So and y2x means y2 is 1 minus x into y1 t, y1 is x, so y1 t is t, and it is matching with option 1. If you don't watch that video on Green's function, then you will not be able to understand this. Okay, there I have described it elaborately. Okay, so go through that video. The link is given in the description. Now Question number 8. The solution of the first order differential equation dy dx plus 2 by x into y equal to f of x may be written in the form y of x equals to c to x, where c is any constant, g of x prime f of x prime dx prime, where y of c equals to 0 for c belongs to real numbers, or the Green's function g x prime is given by. So this is basically first order differential equation, and this is the solution y of x. So to solve this type of differential equation, what we generally do, we find integrating factor. So integrating factor, the formula for integrating factor is our integration px dx. Px is the coefficient of y, so px is here 2yx. So it is over p dx means x square. So we have to multiply both sides of the equation with the integrating factor x square. So what we did, x square dy dx plus twice xy equals to x square fx, and it can be written d dx of x square y equals to x square fx, which may be separated and integrated using y at c, the boundary condition y at c, or condition y at c equals to 0. Using this boundary condition, we get x square y, and taking integration on both sides, you get c to x s prime square f of x prime dx prime. Now we have to compare it with this y of x. So y of x equal to x prime by x square f of x prime dx prime. So gx x prime by x into whole square. So it is matching with option 2. Okay. Now moving to question number 9. The Green's function satisfying d square by dx square g of x x naught delta x minus x naught with the boundary condition g minus l x naught equals to 0 equals to g l x naught is. Okay, so what we do to solve Green's function problem, we just write the homogeneous form. Okay, and the situation is given like this. So we are calculating the solution in this limited region. So as I told you in the Green's function video that using Green's function method we can only calculate some solution on some fixed region, not on overall region. Okay, so this is the region minus all L to L, and x naught is some arbitrary point between these 2 points. So the solution of this differential equation can be written in terms of this, because we have written in terms of 4 constants, because we have to find out y1 and y2, means 2 function on this side and on this side of this point x naught. So this y1 and y2 is determined from the given initial condition. So we have to utilize this. G of minus L x naught equals to 0, and G at L x naught is also 0. So G and minus L x naught we get minus. So these are the y1 and y2. So what we have to find out in solving Green's function, y1, y2 and constant a. Okay. So here we have written y1 and y2 in terms of these 4 constants. Now from the given boundary conditions and properties of Green's function, we have to eliminate these 4 constants. So first we are applying these boundary conditions, and we got 2 relations. So from 2 relations we can remove 2 unknown constants. Okay. So using these 2 conditions, we removed 2 constants b and d. Now to further remove these 2 constants a and c, we are applying the continuity of Green's function. So Green's function is continuous. Okay, there is no overall discontinuity. So we are applying the continuity at x naught. So a into x naught plus L equals c into x naught minus L. So a equals to c into x naught minus L by x naught plus L. So we have got this. So we have written one constant in terms of the other. Now we have to know another constant. So we need another condition or boundary condition. So from discontinuity of Green's function dg dx at this point x naught, dg dx at x equal to x naught plus minus dg dx by x at x equal to x naught minus equals to 1. 1 here, the discontinuity is equals to 1 by p of x, but here p of x is 1, so 1 by 1 means 1. So we just did taking derivative with respect to x here, so c minus a equals to 1, so c equals to a plus 1. We just put the value here and we got a equals to this. So a is found in terms of the known parameters, and accordingly c we got in terms of the known parameters. So as you know, this a and c will just put this value here, and g is involved with the unknown constants, and we have found out all the unknown constants, so we got g like this. What is this? Some mosquito. Okay, and it is matching with option 1. Finally, question number 10. The discontinuity in derivative of Green's function g of x naught associated with the differential equation x squared d square y by dx square plus twice x du dx equal to x square with u at 0 equals to 0 and u at 1 equals to 1 is. So this is the differential equation we are given, so we just write. So in the previous problem we see that we had to multiply with integrating factor, but it is straightforward. So d dx of this equal to x square, and px is given to be x square here, px equal to x square. Now we have to find out the discontinuity, so we did this to determine the px. So the discontinuity is 1 by px at x equal to x naught, so 1 by x naught x square. Basically this problem is very easy. Okay, so it is matching with option 4, so option 4 is the correct option, and this is the end. So I have tried my best to provide the solutions in great detail. Irrespective of this, if you have any doubts or confusion, you can comment down below. I will try my best to clarify them, and any kind of suggestions are always welcome. So this is all for today, guys. If you find this video helpful, please give it a thumbs up and make the like button blue, and if you are a new visitor of this channel, please subscribe the channel and press the bell icon so that you never miss any update. Keep sharing and keep loving in this way, and what I say at the end, thanks for watching.